Hello, good afternoon. Welcome to the stream. It is, as I said in my announcement, a rainy Sunday, so I guess that means I'm not doing anything outside really. But we're here. We're going to do some more compiler construction in Gleam following the book Essentials of Compilation. If this is your first time here, welcome. Thanks for coming. And it's going to be a bit diving in the deep end if this is your first time here, so bear with us. But we are currently in chapter 4 of the book. Again, Essentials of Compilation is a textbook designed for a class for building compilers, and it goes from the bottom up. So you're starting with very simple languages. You're building many intermediate forms, intermediate representations. We're calling them languages in this because they are kind of languages in their own right. And you're doing small passes to transform one into another to the point that we actually get x86 assembly. And so we are going from top to bottom, adding new features to our high-level languages and propagating them through the low-level languages until we get to x86 64 assembly. And so we're in the middle of adding Booleans and conditionals to our set of passes and languages. So what we're going to do is we're going to jump back in, and I think that what we will do is see where we were last time, and then we'll move forward. I said that we're in section 4.10. So yeah, it's all about register allocation. So let's switch over. Reminder: if you want to follow along in the code, this is where I'm sharing it. Sean Cribb's Essentials of Compilation. Again, we're doing this in the Gleam language, which compiles to the Erlang virtual machine as well as to JavaScript. And so at some point we'll do a fun side project and make our own little playground or compiler explorer from the Gleam sources compiling to JavaScript, which will be really cool. But right now we're just using the Erlang virtual machine, the Beam. Okay, so there's one small thing here I didn't commit last time. It's just removing an unused import, so we're not going to worry about that. But if we look real quickly at the log, we updated uncover live was the last thing we did. We had a contribution. Thank you, Michal, for fixing RCI, which is updating Gleam to the latest. And yeah, so we fixed select instructions. We updated uncover live, which is really just doing the liveness analysis for every block. And I think that we probably didn't change the tests here. So we probably need to make a new uncover live test, which covers it covers branches. So let's come up with a possible set of code that would be would update the liveness analysis on multiple blocks where there's branching involved. Let me see if is there something that we can easily craft in the intermediate language. Now that, remember, this is operating over this x86 var if language. So we're close to x86 assembly, but we're not quite there because we still have variables. And if we look at what's in the language, it's a set of blocks, named blocks. We have instructions here, but we have this jump if, which compiles down to the various jump conditionals that x86 assembly has. We have an unconditional jump as well. And then we have the typical mathematical things like add, subtract, negate, the memory stuff, and populating registers with move, push and pop for stack manipulation, calling to other functions that are defined externally. And then we added the, hi Chris, nice to see you. We added the XOR and the comp, as well as the set. These are, and move ZBQ. These are all about implementing comparison instructions. So comp Q is the comparison. Set is like, I'm going to check the flags register for whatever flag I'm asking for here. So this would be like greater than or greater than equal, etc. So there's various flags based on the result of this comp Q. And then that puts it in a single byte register, which would be like AL probably. And then this move ZBQ is used to transfer the byte register into a 64-bit register. So a quad word register. That's what Q is for, quad word. Okay, so those are the things that have been added to x86 assembly. And so that's what we're operating over in this uncover live pass. And we adjusted this last time such that we needed to make sure that we constructed the order of dependencies in blocks so that we would process the liveness, because it's always based on going backwards. So you start at the end of the program essentially, and based on the architecture what registers are live at the end of the program. And it's basically going to be like RAX and RSP, because that's how the kernel jumps into your program. Is it says initializes. There's probably a prelude that comes from the operating system, but it essentially jumps to your main function after setting RSP, and then it expects RAX to be like the return value, right? So the exit code or something. Anyway, we're kind of glossing over that because there's some runtime bits that we're not implementing right now. But we know at the end of the program, RAX and RSP will be live. And so then you work your way backwards looking at what things does this instruction write to and what does it read from. And then it adjusts the live registers so it goes backwards from what was after, and then it adjusts it to you get what was before. And that before becomes the after set for the previous instruction, and so forth, and you work your way back. Well, the problem is when you have conditionals, you have to jump between blocks. And so their live after sets are not all RAX or RSP. They're dependent on what they jump to next. So we built a topological sort of the blocks in the body. And then we use that set of indices to fold over the contents, recompute the live after, and then insert it into back into the dictionary. And that's what this uncover live pass did. You'll note here that in this build config order, we fold over that, adding vertices to the graph as we're building it, and then if we get a arbitrary jump or a conditional jump that goes to conclusion, which is what we'll be generating in a later pass, that's the bit that adjusts all of the registers according to the calling convention after we're done. So it pops the stack, it resets the base pointer, and so forth. Then we don't, if it's not a conditional or unconditional jump to conclusion, then we say that there's a dependency between this block and that block, and then we compute the topological sort. So that was basically everything. So this is a module that we created last time, the context context flow graph. Anyway, CFG. And it just calls out to some Erlang module that we created. And we could also in here put a JavaScript module. I did look up one that we might be able to use that has topological sort in it. So this is a fun sidebar into how do you do FFI in Gleam. Okay, so that's where we are. We need to come up with a simple program that will demonstrate computing the correct live after and live before. And we probably need to do that by hand so that we can make sure that we're getting the right stuff. So that's not going to be especially fun here. There aren't examples in here that we can just use, I don't think. Yeah. Okay, remember the book is about doing it in Racket. There's also a version which is Python, but we're using Gleam, so we have to kind of translate things wherever we can. Okay, so let's just try our hand at a test. Live with branching test, and let's see. So let's make a program. We're going to make an x86 program. And we're going to make some blocks here. Okay, so we're going to have a start. And let's do this thing like we did. We need to... Yeah, this is what we want. So we're going to make a block here, which has it starts from base block. And we're going to do this with all of the blocks that we're creating. And it might make sense to make some sets of instructions up here. So let's write the start body separately, and then we can construct this program from the individual pieces. And maybe what we'll do is we'll do something where let's do, this is readint 0, and I think we had an example of that. Yeah, we did this. Okay, and then we're going to do add immediate 42. How did we do this up above? Yep. And register rex. I need a comma there. That's what's wrong. Okay, so we're going to read. And then we're going to do comp. We're going to compare I think we'll just do equality here. We're going to compare an immediate 0 with register rex. And then we're going to do jump if, and we need to get, yeah, I think we need to import all of those. Yeah, because those are what are used in here. We'll just import EQ for now. Okay, so we're going to compare. Oh, we need a comma there. And then we'll say block 1. Okay, so I need to import jump if. Okay, so we actually need to not import this one. We need to import it here. And then we need to import comp. It's comp q, I'm sorry. Right? Comp q. Why is that not in scope? Did we put that? Oh, it's E. It's not EQ. Okay. Let's fix that. All right. Don't even know the stuff that I wrote. Okay, so what we're thinking of is this the C-like program would be like actually, because we don't. Let's do a move q because we want this to be a variable. We're going to move from register, because this is return value of that function, right? Into var of a. Okay. And then rather than using rax, we're going to use var a here. Because we haven't assigned registers yet. We know that rax is the return value from a call. So if our C-like language had call and assigning it to a, then we have this move from rax into a. Okay, so if it's equal, we'll jump to block 1, and then we need an unconditional jump afterward, and we'll say that goes to block 2. 1. Here, why don't we just... We're going to rename this to start. Okay. So block 1, let's just have it do what is essentially a return. That would be, it's going to have a move q from, let's say, immediate 0 into register rax, and then it's going to jump to conclusion. This is how our high-level returns will be translated. And then block 2 is going to do something similar. Maybe it does move q from var a into rax and jumps to conclusion. Okay. So I don't know that our generator will generate this, but what we can do is we can start here, and we can make assessments about what's live, right? So here rax and rsp are live. Hello? Okay, I want this. Okay. And here we have, so the rule is, for the before set, you take the after set and you subtract the places that are written and then you union the places that are read. So what we're expecting here is that we subtract rax and then we have a. So we have variable a and rsp. Okay, and here we also have rax and rsp. And we have rsp because we wrote into rax. So we know it has to be not live before this expression, before this statement. Okay, so how does the rest of this go? So we have this instruction here. Its live after set is this, right? And this instruction here, its live after set has to be at least RSP. So It honestly doesn't matter where we start here. Its live after set on this jump is A and RSP. And I think what this, because jump instructions, I think it just unions them, if I recall correctly. So let's look at, okay, so read instructions, write instructions. Yeah, those are unmodified by jumps. Right, so we do have to pass the blocks in here. And if we, right, so if we start with the assumption that RX and RSP are in the live set, right, so if it's a, so this is getting the previous, the live after set, right? If it's a jump, we just assume it's the live after from before. If we're jumping to, sorry, if that's jumping to conclusion, that's the end, right? If we're jumping to another label, then we get the live before set of that block. Because we did the topological sort, we can assume that this has a live before set that makes sense because we processed it first. And then if it's a conditional jump, then we union the live before set of the destination and the statement that comes after. So, or instruction, excuse me, we're in instructions. So this is what I expected. So here, this will be the union of this set, which is ARSP, and then this set, which just has RSP. So the result here should be RSP, A and RSP. And this comp reads from A. Sorry, I need to remind myself of the rule. Okay, so it unions with the reads and difference with the writes. So subtract the writes. There's nothing written to here because we don't track the flags register. So we're still with A and RSP because A was read from. Here, A is both read from and written to. So it still exists in the set. Here, A is written to, so we subtract it. And we put RAX back in there because RAX is read from, right? And here we have nothing read from, but we have RAX written to by the call. So here RSP is live. Okay, so I think what we can do is let's construct these blocks. Oops. So we have dictionary from list. We're going to say block 1, and we'll have block, base block, and the body is block 1, and we'll have block 2, block. If you're not familiar with this, this is the update syntax for structures in Gleam. This will copy the original and modify with the things that follow. So block 2. Okay, so there's our initial program. Now we're going to I'm not going to assert what the program is because the contents of the instructions is not changing in this step. We're just figuring out what the live before and live after sets are. So I don't know that I want to check every single one, but I do want to check the before for every block. So let's say P2 is uncover live. Yeah, interesting to see the effectively opposite choice from Rust, etc., in terms of ordering the struct update syntax spread. Yeah, that is interesting. I don't know why that is. It could be that. It could be that like Elixir does it this way in a sense. Its map update syntax has the original and then the bar and then the extra stuff. I think I could technically put it on the end, but I've always done it on the front. Which actually, if you think about it in terms of order of operations, is probably desugared to, you know, base block and then set this field. If I put it at the end, it might happen the other direction. I'm not positive though. Okay, so what I want to do here is go I want to say let's do let assert yeah, we'll do okay is, and then this is, let's just use S because I don't necessarily want, I'm not trying to pattern match here. I don't think that that does that, but I want to make sure we don't accidentally pattern match. We're going to say p2.body. We're going to dict get start. Okay, so then we're going to say s dot live before should equal set from list. So we know up here it's just going to be RSP. And we need that to be in a list. What did I do wrong here? It's location reg. Yeah, there we go. Okay, so let's duplicate this for each of the other things. So we're going to say block 1. And we'll say B1. And what did we say the live before should be? Should be RSP for block 1. Okay. And for B2, here we had variable A and RSP. A. All right, let's see how badly I did this. Hey, we actually walked through the algorithm by hand, and we got the right answer. So, okay, I feel pretty good about this now. Let's make a commit here. Honestly, I should be writing the test before I write the code, but we're not a purist stream here. So we're going to have additional tests for test for Uncover Live with branching. Yeah. This is what it's like to work with me. God, I did that wrong, and then it works. Because I am apparently lucky. Okay, so now, not there, this. So we updated the Uncover Live. Building the interference graph, I think, requires very little, but let's look at that. Because we need to adjust for the new instructions. So they're saying it needs special care similar to move. So let's have a look at that. Let's look at the tests that we have so far. Okay, so what we were doing is we were building a set of instructions and the live after set. And then building the interference graph on that. And we were not really checking what the structure of the graph is, but like going, does it have a conflict between these two things, right? And here we did it with calls. So maybe what we should do is have, maybe we can use our new program that we wrote here, and then we can, yeah, let's do that. Let's go ahead and make the test, and we'll probably have build interference with branching. Test. Okay. I don't know. We didn't import Uncover Live. I think that we were manually constructing this stuff. So knowing that this previous test passed, here, let's make sure we get to the jump if. We're going to need to be able to test moves EBQ. We need comp Q. Because that requires special handling. So let's import Uncover Live. Here. Where the heck? Oh, I accidentally did multi-line. Uncover Live. Okay, so now we have that in there. And what we want to do is pipe this to build interference. Okay. So one of the things that we might have trouble with, and I'm not positive about this, but we were previously putting the interference graph on each block. And I don't know that it should be there. It might need to be at the program level. But in the meantime, so we know that this corrects constructs the correct before and after live after sets. So we can do, what did we do here? Right, so we can do something like this. We build the interference. Okay, and then we get the conflicts for each block. I have a suspicion that there will be some kind of inductive property here where if we are maybe that's not true. I wonder if we need to process this in topological order as well. or if it needs to be one graph. The thing is, though, I think that okay, here's the problem I'm wrestling with. Those jumps are not necessarily independent of one another, right? So, like in our example program here, we use this variable a in the start block, but we also use it in block 2. So these need to be the same location across those jumps. And then if there was any expectation about what the contents of a register were in this jump or variable, that needs to be accounted for. So I feel like we need a single interference graph for the entire program. As long as we have only essentially one function we're implementing, right? One expression. When we get to later in the book, I think it's chapter 6 or 7, where we actually implement functions you can call, then it gets a little bit different. But for this sake, for this phase of our evolution, I think we need to consider the whole program, because it is just one function, essentially. So a variable that is defined in one block can be referenced in another block arbitrarily, as long as it's live, right? Which down here, it's live. So let's look at what the book says here, right? Okay, so we need to adjust these instructions. Okay, so let's look at build interference. I'm actually surprised it's not broken. Okay. So determine conflicts is constructing a new interference graph for each block. Okay, and here we're dealing with these two rules, right? So a move from source to destination. Okay, so we're taking the set of locations in the source, we're unioning the set of locations in the destination and the live set, and then we're adding locations to the graph. So if we go to this is just fold over the locations, inserting them into the graph. So if it has a node, it just returns the graph. Otherwise, it inserts the node, and this node, okay, so it has a location, an optional assignment, and then the saturation is like, what are the other things? And this integer here is like an index into the registers. So yeah. Okay, so insert the location, inserts a node. Okay, so that ensures that every source and destination is in the interference graph. And then it folds over the live the live after set. It says if it does not contain, if the source set does not contain, a location. I should rename that variable to location. Let's just call it loc. Okay, if the live after set does not contain the source and does not contain the destination, then add a conflict between. Okay, so this is adding a conflict over the destination, which is just going to be 1. There's only going to be one thing in this, there's only going to be one thing in this, but we have to use sets for the union case. Okay, so it's going to add a conflict for the destination. With that location. Okay, so that's rule 1. Okay, so basically that's saying this rule says we're writing into destination. So destination cannot be part of the live after set, the known things that are live after this. No. That's reversed. Is it the live before? Okay. No, it's the live after. All right, let's look at rule 2. Rule 2 is anything else. I think this is the way it is because we might have to go back to chapter 3 to look at this again to understand it. Because I remember this being kind of complicated. But let's look at rule 2. So rule 2 is like for any other instruction. So we probably need to handle move ZBQ, especially like we did for move Q. And essentially there will be a source, but we can't represent that source in our graph because it's not something that we can assign to any variable, right? So we'll put in another rule 1 and we'll put the source as empty. And then for hi Amos, good to see you. And then we'll have to handle set as well, I believe. We might have to handle set especially. But if we go here, write location and instruction, yeah, it's an empty set here. It's an empty set for comp Q. And move ZBQ. Well, that's interesting. We could, because we only care about the right locations, we could honestly just use this directly and not have to handle move ZBQ especially. Because we only care what it's writing to. Interesting. Okay. We might be able to just, because we only use move ZBQ when there's a comparison and we need to store that result into a location. Like if you said, oh, I'm going to do an assign, like let x equals some Boolean expression, and so x is a variable that will be used, and then Later on, you do like, if x and some other Boolean expression, well, x has to be stored somewhere in the meantime. We're not doing any like rewriting where the expression will be inlined or anything like that. So honestly, I think that this still handles it. The problem is that, like I said, we're not building a whole program interference graph. And I think that what we need to do is build a whole program interference graph. Let me look at the text again and make sure that I'm not completely off here. This maybe goes back to, we'll look at 3.3. And possibly the assumption that the interference graph is in like that info A list in the program that we don't implement because we have to name every field. And we put it on blocks for convenience, I think. The thing is, though, if you look at these other tests, well, other test, singular, we only had one block. So I don't know if there's... what I'm trying to say is that this probably is another assumption that we need to challenge and rethink, like we've done multiple times in this chapter. So if you all have any objections to me making a whole program interference graph, speak now. Otherwise, I'm going to do that because I think that that's the right way to go, which means that we're going to have to drastically change this. Here, we don't need to see the build directory right now. Okay, so I think this... Woo, refactor, yeah. I'm a little scared. I'm not gonna lie. I'm a little scared. We're gonna do this, and we're gonna have to make something like this, and we're gonna remove it from the block. And let's see. Do x86 program. And I'm probably going to blow up all sorts of things with this, and I'm not real excited about that. Body is dict new. Can I type new? Okay. Conflicts is this. Okay, and now that's going to break all sorts of stuff. So uncover live. What we'll do is we'll call this new blocks is that, and then we're going to say we'll do dot input. Body is new blocks. Okay. And then since we're not piping that into the constructor again, we're going to do like so. And then there's going to be a problem in that previous phases. Yeah, select instructions is the one that turns it from the C-like language into the x86-like language. So we're going to have to go new program and maybe don't really like doing it like that, but interesting. Nothing else blowing up. Okay, so then we have it in here, and we're just modifying the input program. That's fine. Okay, so then here in build interference, we want to change this so that we'll do something like we did before. New conflicts is, and this is not going to be dict map values, it's going to be dict fold. And here we're not so there is no conflicts field on the block. What we need to do is let's just rename this to conflicts. Okay, this is not returning the right thing, but what we need to do here is we're going to take, let's change this to fold. We're still folding over the program body, but what we're going to take is the initial conflicts as the accumulator, and then dictionary fold takes, okay, so the accumulator, the key, and the value. So this is the interference graph. We don't care about the key. And then what we're going to do is change this to take the interference graph. And in here, this is going to be interference graph. Okay. And then rather than fold over a new, accumulating in a new graph, we'll fold over the existing graph. And I think that's the extent of our refactor there. I hope you followed that. Basically, we're taking the empty graph that we constructed in select instructions by calling new program. And then we're going to build all the conflicts. And now we need to fix our test. Okay, allocate register is still broken. Not that surprising. But here, now that we've changed all that, what we're going to need to do is, why is this not broken? This should not compile. Okay, rather than the block conflicts, we're going to say p2.conflicts. I need to restart the LSP. It is completely broken. I probably have some other error in there that it's not happy with. Okay, here we need to do the same. We need to say p2.conflicts. Okay, and then down here, all right, did I not save this file? Is that what's wrong? No, I did. What's going on? Oh, I messed this up. Oh no, wait, no, list a set of location. It's fine. Okay. Let's Gleam build and find out what's wrong. It surely, yeah, okay, okay. We don't care right now about that. Unused. Okay, so the allocate registers test is broken. Let's comment out anything that honestly I can do this. And this will be body. Okay. Oh wait, wrong thing. Don't actually need to change that. Okay, it's just complaining those aren't used. What are the other errors? Okay, incorrect error. So here we need to fix this. This be body. Okay. And we need to do the same thing down there. So, okay, we're almost there. Okay, so now it's just saying it's not used. So what we can do here is let's figure out the interferences that we'll have. I'm going to start with block 2, and we'll because it's closer vertically, and then we'll work our way back. So has conflict. So, oops. How did we do that? Yeah. Did we? Oh, okay. No, I'm getting that wrong. We alias the module. Okay, so we want to check conflicts. So we know from block 2 that A and RAX cannot be the same. So let's do location register RAX and location var A. Oops, not RAX, no quotes. Okay, and this should be true. And this is, we have move Q from A into RAX, right? And there's no conflict there. A and RSP are live at the same time. We also have the conflict from here, right? Because it's moving from the result of the call into A. So we know that that's true. And move Q RAX into A after call. Okay. The other one that we know is that A and RSP cannot be in the same spot. So as conflicts. This is actually a fairly simple program, but we're covering we're covering the set of live things here pretty carefully. So, all right, I think that's A and RSP are live at the same time. Here, and I'm going to put percents on that like they do. Okay, so I think that that's fairly sufficient. Okay, so we've got some problems here still. Select instructions test. I broke it. We didn't update this one. Don't want to do that. Base program. New program. Body. Okay, where else do we need to do that? And I'm just gonna copy that. I should have done this the same way everywhere. But this is a hobby program. So what am I missing there? I'm missing a paren somewhere. Why do I have two? Oh, I need to remove that one. Then it'll be fine. Okay. And there's probably one more down here. Yep. New program. Okay, that's everything. Let's make sure we didn't leave any errors behind. Okay, so these are all select instructions test, select instructions test. Okay, so let's run Gleam test. We have more. Uncover live test. I didn't get updated. Okay, so we'll do base program, body. This is really not exciting content, but we're gonna fix it. Did I miss anywhere? Yeah. Okay, and then I hope that we still have another hour in my planned session, so we should be able to get through the rest of this hopefully without too much more refactors of this sort. And what's wrong there? Oh, okay, so this is like we removed the, yeah, that was a redundant update. And the same thing here because this is a complete block. All right, so down here we need to do that. Okay. Okay, so that's just warnings. We can ignore that for now because we're eventually going to come back. Okay, so we have a problem, and we have false should equal true. So what's the problem? And this is our test that we just wrote. So there's a question here in my mind whether whether it will just use REX for A. I think it's fairly likely, especially since we don't have a moves EBQ, right, anywhere. A is not live in this block. It is live in this block. And because yeah, A and REX are never live at the same time. So there shouldn't be a conflict. That is interesting. Yeah, because they're, yeah. Right? So I think my assumption here is wrong. The only thing that A should be in conflict with is RSP. Interesting. Okay. That's very interesting. I guess that makes sense in this case because you know, at this point before the move, A was not live, but REX was because of the call queue. And then after that, REX is not live anymore, as far as we know. But A is. They're mutually exclusive throughout the whole program. So there's no reason they can't share. There's no reason they would be in conflict, right? And what will happen in the patch instructions is if we have a redundant move, so like we substituted variable A for REX because we assigned it REX, then these redundant moves will get removed by patch instructions, and this will be one as well, and we'll just have readInt, add q, comp q, jump if, jump, you know, and so forth. Interesting. Okay. So this is a good stopping point. Let's add source and test. We're doing, this is chapter 4.10.2, update build interference. Okay. All right. So I think that I feel like we should do something like moves EPQ, but I feel like it's covered by that rule. I say rule number 1 in section 3.3. Let's refresh rule number 1 before I move on. Okay. So if instruction I is a move instruction with the form move Q from source to destination, then for every location in the live after set of this instruction, if if the location is not destination and the location is not source, add the edge between destination and that location. Which, the thing is, it can never be source because we're not allowing assignment or allocation, rather, of the byte registers. Now, there is a potential here that I do need to handle it. Because AL, which is where we're using as our destination of any set instructions, AL is the lowest byte, the least significant byte of the RAX register, as far as I know. At least that's how it worked in older like pre-64 architectures. So we basically have to treat AL as RAX. Because the move ZBQ, right, that's move zeroing the other bytes from a byte register into a quad word. So we have a problem. We need some way to So we have A, B, C, and D as the possible byte registers. And they're AH and AL. So we can pick the low or the high byte. This is essentially 16-bit. If it were just 8-bit, it'd be like A and B and C and so forth. Let's make a little function here. We're going to call it this. B byte reg. Okay, and this is going to return a register, right? Because what I want to do, and honestly, based on the text of this, I would not know this if I hadn't worked with the other versions of Intel. Heck, I wrote 8-bit Intel in college. That was fun. It's super fun having only 256 bytes of RAM. And I think it was like a 12-bit address register, so, or program counter. So I think you had, I can't do the math right in my head, but you had, you know, maybe a few K of program space. Okay, so what we're doing here is we're saying, even though these have different names, they are occupying the same space in the processor, as far as we know. So what I want to do is, we're going to have to go back and do some things here, but for set and for move ZBQ, we have to consider the thing is, okay, so I was going to say we have to consider what the byte register is as the source. The thing that I'm not clear on is, I think it would be safe to move from a byte register in the same register, zeroing out the other bytes, as with the same register as the destination. I think that doesn't cause a conflict. But when we do, say, a comp instruction and a set instruction, so we're assigning a variable like a Boolean value to a variable is essentially what that's doing. We probably want we want to make sure that that set instruction is not in conflict with something that's live, first of all. And we want to make sure that the following moves EBQ that we're going to do doesn't have conflicts with the source byte register, right? So I think that we need to adjust uncover live. And I think that this is wrong, first of all. And I think that what we want here is let's import byte reg to quad. Okay. Because so read instructions. So for read, we're reading from A. So we want byte reg to quad of A. Let's say from list, right? I'm a little bit concerned that this is wrong, but I want to go with my intuition here, and that I want to make sure that we don't this needs to be location register. I want to make sure that we don't introduce something that could create a problem where we have, like, let's say we have a variable put into RAX, and then we do comp q on something else, and then we do move ZBQ, or we do set, right? And we assign something into AL. Now this is the read, right? We're not. This is the read set, so we don't need to deal with that here, but we do need to deal with it down here. So comp q doesn't write into, it writes into the flags register, right? But set we need to do from list. Arg. So that we can make sure we don't make these overlap and blow things up. Okay. I think that this covers the concern that I had. I mean, another thing that we could potentially do is, if I'm wrong on this, and I might be really wrong, but if I'm wrong on this, then we need like a byte register location, and we need to show that those can conflict with things, other things, right? But my gut feeling is that these byte registers overlap or like a sub portion of the full quad register, and that we need to treat them like that. And so they are essentially the same as, AL, AH as the same as REX, which means this is probably going to break things. But we don't have a test covering this yet because we didn't create one where we had assigned something some Boolean expression and then use it later, right? Okay. If this passes the tests, I'm going to expect it to happen. Yeah, because we don't cover it. But now, if we have the source in moveZBQ treated as a register, then we can actually apply rule 1, right? So let's so we're going to say rule 1, and then we have to treat this specially. The thing is, this is always a byte register, so we need to turn it into a location. So we need to do uncover live locations in arg. And the thing is, no, we can construct this directly. So this is set from list location register byte reg to quad of S, and then we reuse the locations in arg for D. Oops. And live. Okay, so what's wrong there? We need to import that. We can do x86 base. Right? Okay. We've done this a lot. I might consider and the other thing here is that we need to consider set. If we're going to do this and treat the source as a byte register, we need to apply rule 2 to it. So if we've got the set instruction, well, no, actually that will still apply because we updated write location in instruction to handle set. So we don't actually have to change anything there. Okay. I think this is still not going to change anything. Yeah, because we didn't cover this refactor. Okay, so we just updated build interference. We updated uncover live. So we need something to exercise these. So let's come up with a program that we can use in both of them. So uncover live, assign Boolean var test. Okay. So let's do. This is going to be a bit tedious again. Let's copy this program and we're going to make some modifications to it. So what I want to do is something like, let's say a variable x is, honestly, let's just leave this out. And we'll figure out what we want this to be in a minute. Oops. Okay, so let's have a variable x is, this is going to be done, true, okay? And then we're going to do if x, again, our compiler has no inlining, then 1 else 2. It's like this sort of thing. So what is this going to look like? This is going to look like move q into var x. We're going to move to immediate of 1 because 1 is how we represent true. And then we're going to we're going to comp q, and I think the left-hand side gets put on the right-hand side. So we're going to comp q1, again, this is a done program, of var x. No, this is not what I wanted. Trying to think of what are the constructions in elif that we can use. Ah, right. So we need a comparison, like as an instruction on its own, right? So it's a primitive operation. We're comparing, and let's compare like just equal for simplicity. I don't think we're doing any partial evaluation up at this level. Yeah, okay. I don't think shrink is going to look at immediates, and no, it doesn't do any partial evaluation. So we're probably fine. Okay, so let's go. Here, I thought we were going to finish this chapter, but we probably won't. Okay, so what I want to do is do something like 5 is less than 10, right? Which is going to be true. So what we're going to do here is we're going to do comp q immediate 5. We're going to do immediate 10 with immediate 5. Okay? And then we're going to use set. We're going to import So we have the set instruction. This is going to do set less than, and it's going to do AL, right? Not elif. This is less than, right? Okay, and then we're going to move ZBQ. Move ZBQ. Let's import that. Move ZBQ. This is the worst. It is so frustrating. Okay. Okay, so move from AL into var x. Okay, so now we have this expression. This is what this expression should compile to. And we don't actually care if 5 or 10 are just, we don't actually care. Okay, so now what we're going to be doing is we're going to do a comp q of immediate of 1, because that's true, with var x. And then we're going to do a jump if equal to block 1, and otherwise jump block 2. Whew. Hello, Sculpt W Stellan. Okay, welcome to the stream. Okay, so here we've got a variable which contains a Boolean value, and then we're using that in a branching instruction, right? Okay, so now, and the main thing that we're trying to test here again is set and move ZBQ, right? Because these involve byte registers which overlap with our 64-bit quad word registers, right? Welcome from India. Glad to see you here. Okay, so here, we're doing if it's true, then we're moving to register RAX, and then we're jumping conclusion. Okay, and then block 2, we are moving immediate 2 into register RAX, and then we jump conclusion. Okay, so let's do the live after sets for each of these. It should be straightforward like we did earlier. So we've got here, we always start with RAX. Oops, let me get comments out here. We always start with RAX and RSP because those are the return, right? The return value and the stack. So here we wrote into RAX. So we remove RAX from the live. This is the live before set. Yeah. So jump doesn't change, and I should, for clarity, put RAX and RSP are after. So this is the after. This is the before. Okay, let's do the same here. And actually, this is exactly the same because they both basically do the same thing. Okay. RSP, and here it's RSP. Okay, so that means that this is the live before set for this instruction. So that is the live after set for this instruction. And this one, because it's a jump if, takes from both of them. So it takes from the instruction that comes immediately after and the thing that it's jumping to, which is this. So they're both also RSP. Here, we wrote to X. No, we didn't write to X. CompQ doesn't change any of this, but X should be live here because it's read from. Okay, and then here we have, so X is live after this. We subtract X from there, and AL, so we have RAX and RSP. And we need comments there. Let me outdent these some. Put those out in a column to the right. And it's, I know the formatter is going to mess it up, but that's okay. Okay, so because we read from RAX, so that gets added to the live before set. The variable X is written to, so it gets subtracted from the live before set. And we have RAX and RSP. And here, we write to essentially RAX, and we read from nothing, so RSP. And here, just following that, CompQ doesn't change anything, so RSP. So these should be our live before sets. And you know, you can inductively get the live after. So what I want to do now is we're going to construct the program like we did up here. Let's just copy that. We need a base block. Okay, so we've got start, block 1, block 2. And then we're going to do uncover live, because that's what this test is of P. This is how we did this one? Right, okay. So then we're going to do something like this, and we're going to check the live before sets and make sure that they're equivalent. Okay, so for start, it's going to be RSP, right? And for block 1 and for block 2. Interesting. Let's look at let's first of all make sure that those assertions pass. They do. And then maybe we can get this a bit more detailed and go like look at the third and the fourth. Because we want to see, well, look at the second, right? Because we wrote to RAX essentially, and so we want to make sure that it's not in the live before. My brain's getting twisted here. It will be in the live after for this, and it will not be in the live after for this. Okay, so let's look at the live after CompQ will be RSP. Okay, so let's say, what can we do with the lists module? Oops. Does it have an nth? The other thing I could do is say pattern match on it. So we could do let assert and there will be the same number of items in the list as are in the list of instructions, the live after sets. So come on, cat, getting in the way. Okay, so we're gonna say this is the live after for the comp instruction, this is the live after for the set instruction, and this is the live after for the move ZBQ instruction. Right, I was writing the live before. Okay, so we can do this is s.liveAfter. Okay, and then we can do set contains, we don't actually care about the comp. So, oh, and I should call this set instruction. So set contains takes the set, and we're going to say that RAX has to be in that after set. The other thing that we're going to say is that for that set, it should not contain be false, right? But it should contain the variable x. Should be true. Okay, and that's just a little bit of sanity checking here. And okay, so that does pass. Our algorithm works the way we think. We've covered the fact that that the RAX and the byte registers AL and AH are basically the same register, and so they are in conflict. You can't you can't have overlapping lifetimes of them. Hey, guess what? This is basically like lifetimes in Rust. If you understand lifetimes in Rust, you understand this. Mostly. It's a bit lower level. Okay, so now that we've added this, yeah, I figured you'd get that one, Chris. Okay, so now we need to do this test in the build interference, and I think that we're probably not going to find anything remarkable, but let's go ahead and make the test for that. What did we call it over here? We called it uncover assign Boolean var, right? So build interference, assign Boolean var test. Okay, so we're going to put this in here, and we're now going to do p, and it's going to be build interference. Okay. So we're just reusing what we did in the previous test. We're not going to bother like manually populating those because we've already made plenty of assertions on that. This is the same exact example. So now what we want to do is show that really the only interesting ones are X conflicts with RSP. Obviously, the registers conflict with one another, but they can't honestly be allocated, so it's not that interesting. So let's do conflicts is p2.conflicts, and then we're going to say has conflict of register RSP and the variable x be true. That's the only interesting thing here. We could check that RAX and RSP have conflicts, but that's not interesting because we don't try to assign, like, registers are already assigned, right? They get inserted into the graph being assigned. All right, what's wrong with this test? It looks like it's not compiling. Okay, ignore those for now. Ignore that for now. Okay, so we need to import set and move zbq, and then that should compile. Okay. All right. So we have we have 15 minutes left. At least with my plan stream. I might go longer if we're really, really close. But I think that we probably need to... Okay, let's go back to chapter 4. Okay, so we handled interference graph just now. Okay, so these we have to do stuff in patch instructions. Okay, so honestly, we built an invalid program. Okay, so compq cannot be an immediate value on the right-hand side. That's funny. Maybe we should go back and, like... I wonder if we did that in the select instructions. Did we handle that? I mean in the code. Okay, so this is the thing that we covered earlier. And actually that's okay for this phase. I think it's the patch instruction. Right, we didn't implement the partial evaluator. So, at least not, yeah, we didn't do it for elif. So let's make sure that allocate registers will work. And we need to do basically this, right? Because we we're gonna have to do surgery on this as well, because we put the interference graph at the program level, and I think we need to color the graph and extract the assignments, right? And then we rewrite the instructions. Okay. Well, let's go for it. YOLO. All right, so we need to do the, oops. We need to do this here. So, what is this used callies? Oh, okay. So we need to treat this at a higher level. The block doesn't have, well, x86 int block might have this. Yeah, it has the stack vars and the used callee. So that's going to be interesting. Honestly, at this point, since we have only one entry point that requires stack manipulation, these can be the same on all the blocks. But I think that we need to... Oh, wait, but we're not translating to x86 int. We're translating to x86 if. So let's fix that. Okay, so that also changes some things. We're going to have some interesting things in the prelude and conclusion, obviously. But let's pull, because the conflicts are not... Right, see, this is the live after set. And this is the live before. So we need to pull this stuff out. Let's do let assignments is input dot conflicts, right? So we're basically doing this, and then we need to compute the used callees and the stack size. And all of this happens up here. So, yeah. So let's pull this out. Okay, and then what we're going to do here, because this becomes a lot more simple, we don't need all of this, right? Let's pass the assignments, yeah. Or let's inline this. We don't need this extra function, right? So what we're going to do is just put that in here, and we'll say block dot body. Okay, and then we can get rid of this function. We don't need that. Okay, so all of this stuff now happens at the program level, which we expected. And now we just need to fill in the patterns down here. So we'll add missing patterns. And we'll do... and these need assignments. Okay, and then this is a straight translation. This is move. Okay. And here set, we do int.set. And one of the things that's, I don't know, interesting or nice about this is that we structured it such that there are like really repeatable patterns as we add features to the language. Okay. Oh, and these need assignments. And then I think that, yeah, there's nothing to change there. I don't think that this algorithm needs to be changed at all. Now there's a little bit of unfortunate bit here that I think because we moved the interference graph to program level, it's kind of making me want to move oh, actually this doesn't change. That's a bug. It kind of makes me want to move the stack size and the callee assigned variables to the program level, if that makes sense, because we care about that when generating the prelude and conclusion, but there might be later when we are implementing our own functions, we might have the possibility of groups of labels. So like a function, which could be the entry point function of the program, translating to a group of blocks, such that that has like a start symbol, and then the group of blocks, they're just named arbitrarily, except the one that has the start symbol, and then we have a prelude and conclusion for that group. I don't know. It'll be interesting to see how it evolves, but I'm seeing that there are more things that need to be kind of pushed up to a higher level that I had been treating on blocks because we had only one block. So let's look at x86 if, and maybe, yeah, let's for now move these onto the program, and then that will make, oh boy, where did it go? Allocate registers. So that'll make this be simpler. Okay. Da, 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 da. What did I do wrong there? Stack bars. Let's name it the same thing. Okay. Okay, and there's actually no, other than fixing the test, there's like no harm in doing that, I think, because here, this is like a full program. So let's go and fix the tests. And here we're going to be okay, so we'll say this is body. And then we'll have stack vars is 0 and Kali saved is that. Oh, except I need to update this to x86 if. Okay. And then we didn't do used Kali. Oops. We didn't do any other tests. Okay, so we're going to have to do some stuff with probably porting some of our tests that we did for build interference on Cover Live to allocate registers. But what I want to see here is that with this transformation, we didn't introduce anything new. So let's go ahead and test. Yeah, we didn't introduce any new bugs there with that change, but we did restructure it such that the block doesn't have anything but the instructions in it, and then these things are up at the program level. Obviously, it does mean that the following phases are going to use different things. So patch instructions takes, yeah. So we need to switch this to x86 if and handle that. I think that we're going to have to bump to next week to finish that. But let's make a commit here. And let me look at the diff. So, okay, so we did a number of things here, and I probably should have made an intermediate commit. Okay. And this is, we're basically doing 4.10.2. And we're going to have treat byte reg as overlapping with the quad register, and then update allocate instructions. And that's a good place to stop for the day. Next weekend, holiday weekend in the United States. But the holiday is on Friday, so I will be here on Sunday again. We will get to patch instructions next. So we'll have to handle this comp queue thing. We'll also probably port some of these changes that we made to uncover live test and build interference test into allocate registers test, just to like as a sanity check, right? Because I want to do some things like see that, we covered that these things are not in conflict, but I want to see, when we do this program, does X get assigned to REX, or does it get assigned to something else? So that'll be fun. And thanks for coming and participating, and hope to see you next week.